Okay, welcome back. We're going to have another R session now. And today we're going to explore fitting nonlinear functions using R. And once again, we're going to actually work within the RStudio Markdown environment, which I showed you last time, which allows us to document what we're doing and produce a nice web document that records everything we've done, the output of our function calls, and the graphics that we produced. So this is a very easy way of documenting sessions in R, both for yourself and people that for whom you're doing the analysis. So in we go. Just to remind you, if you want to learn a little bit about R Markdown, if you click on this button over here, up on the right, you'll get the help, and it just gives you a very brief overview of all the simple commands and ways of indenting, highlighting, and so on. The main things we need to know. Okay, so let's get going. We'll once again require ISLR, our library with data sets, and we'll attach the data set wage, the data frame wage. Okay. So the first thing we're going to look at is polynomials, polynomial regression. And we'll do a regression of the response wage on age, and we'll fit a fourth degree polynomial. Now, normally that would require building up a matrix with columns x, x squared, x cubed, x to the fourth, and then using your regression function. Well, this is where R really comes to the fore. We have this lovely formula language which lets us just in one equation here, we've got a function poly which automatically generates that basis for us, and we tell it to take as input age, and 4 is the degree. That'll make the matrix, and then LM will fit the model with response wage, and so it just all happens for us. Okay, and then we do a summary of the fit, and you'll see below we get the summary, sort of short on space here, but the usual kinds of summaries that we get from LM. We get the formula, summary of the residuals, and then the coefficients. And we see that the coefficients, they all named poly age 4, and then 1, 2, 3, and 4. This will be for degree 1, 2, 3, and 4, the different degree monomials. The first two are very significant. The cubic is significant, and the quartic is just barely not significant. Okay, so it seems like a cubic polynomial would be sufficient. Now, normally you can't, when you have a whole matrix, you can't just look at these coefficients independently. Usually what it means is the effect of, say, this coefficient in the presence of all the others, and if the variables are correlated, you just can't make sequential decisions. But here it's a little different, and that's because the function poly generates orthogonal polynomials. So it's like we're doing a regression with uncorrelated predictors. And we'll get back to that again in a little moment. What we want to do now is make a plot of the function. We're usually not interested in the individual coefficients of a polynomial, but we're interested in the function that it's produced. Okay? So we're going to go through the steps now of how to actually produce that plot. So we tell RStudio that the next segment is going to have a figure, and well, we need to, if we want to specify the width and height of the figure, we add that in the little opening incantation there. And so now we're going to set up for our plot. So first of all, we want to get the range of age, and so we'll just use the function range to get age limbs. That returns the vector of length 2 with the maximum, minimum, and maximum. And now we use the function seek to make a grid of values of age. So age.grid, we'll go seek from equals age limbs 1, 2 equals age limbs 2. So that's the minimum to the maximum. And by default, seek will just make a sequence of numbers incrementing by 1 each time, unless you tell it otherwise. Since ages are integer values here, that'll just be fine for us. We can execute this. And let's just look at our age.grid below here. And there you see a sequence of incrementing by 1 each time. Okay, So now we're going to make predictions. So we'll predict from fit, and then we tell it that the new data, which has got to be a data frame or a list at least with named variables that were used in the original fit, and since age is the one that was used in the fit, and that's where we want to make predictions, we say new data equals list age equals age.grid. And then we also tell it that we want standard errors. Okay. Your preds now will be a component, a list with two components, and one will be fit and one will be fit, se.fit. Okay. So now we're going to make the standard error bands that we're going to make a plot with a fitted function and plus or minus 2 standard error bands. So here we make the standard error bands. So we're going to make a matrix with 2 columns. So we call the function cbind, which is a way of binding together columns to make a matrix. And it's going to have 2 columns. The first one is going to be preds$fit, so that's the fitted function, plus 2 times the standard error, which also comes from preds. And then the next column is going to be preds$fit minus 2 times the standard error. So that's going to give us our standard error bands. So we send that down to the process. And now we make our plot. So we'll plot age, first plot the data, so age versus wage, and we'll make it dark gray. So there we get the plot. And now we'll do lines we'll use the lines function to plot against age.grid, the predicted function, and we make it in blue. And line width equals 2 is how you control the thickness of the plot. And by default, the line width is 1. And then we use the function matLines, which in this case, we've got a single x, which is age.grid, but we've got our 2-column matrix that have the standard error bands, and you can use a function matLines to plot those both simultaneously. And again, we want them blue, and we say line type equals 2, which means a broken line. And so there you see the fitted function plus or minus 2 standard errors. And so now we're done. So that's typically what we'd like to produce when we fit a polynomial. We'd like to see the fitted function. And it's done for us with a little bit of work. We've had to essentially construct the function and the standard error bands. And we'll see later on that the GAM package has nice ways of doing that for us without us going through all the work. Now, there are other ways to fit polynomials. We didn't have to use our poly function. For example, you can fit it directly. So here we're going to fit the polynomial directly by just specifying h squared, h cubed, and h to the 4th. And so here's the call to LM. Each of the terms separated by a plus. Now, notice we've had to wrap h squared in a function, the identity function. We've seen this one before, I believe. And that's because the power sign, this caret, has a special meaning in a formula. And so if we want it just to mean squared, we need to protect it. And we do that by wrapping it in the identity function. So that'll fit a degree 4th polynomial. And if we do a summary, what we'll see is we see the four variables, h squared, h cubed, and h to the 4th. And the p-values, the coefficients and the p-values are different to what we saw before. And that's because we're using a different basis for representing the polynomials. Right? So if you change the basis, you get different coefficients, and therefore you'll get different p-values. That may sound a little disconcerting, but the real thing we're interested in is a fitted polynomial, and as we'll see, that hasn't changed. Okay? So we can just check that crudely by just doing a plot of the fit from our original polynomial, which we'll just extract by fitted. So it just takes it will extract the fitted values at the given x's, the given values of age, when we fit the function. And we'll plot that against fitted of fit A, and you see a perfectly straight line, which says those fitted values are the same. So the fitted polynomial was the same, but the representation was different. So as I mentioned earlier, by using the orthogonal polynomials, we can test each of the coefficients separately. And and again, if we look at the summary of the fit, we can separately look at the significance of each of those coefficients and decide which ones are not needed. In this case, it was just the cubic. Now, orthogonal polynomials are convenient. They're considered a better way of fitting polynomials. But this idea of testing separately only works if that's the only term in the model. And if it's not a GLM, it doesn't work. So it's got a limited use. More generally, if you want to test whether, say, a 1-degree polynomial is better than another degree, you need to use the more general ANOVA function. And so that's going to be true, for example, if you have other variables in the model. So here we have a simple sequence. Fit A is a linear model just with education. Fit B has got education and age, both trying to predict wage. And fit C is a linear model with education and a polynomial of degree 2 in age. And fit D is the same, but the polynomial of degree 3 in age. So that's a nested sequence of models, nested in complexity. In other words, the second model contains the first as a special case. Likewise, the third contains the second and the first as special cases, and so on. So that's called a nested sequence. And then we use the ANOVA function to sort out which ones we need. And so this is the output of ANOVA. And what it tells us is that certainly age is needed in the model with education. Also, age squared is certainly needed as well as age in the model. But age cubed is not necessarily needed, it's not quite significant. Well, it's significant at the 5% level, but it's kind of marginal. So using ANOVA like this to test nested sequences of models is the right way to go in general. So this has all been using squared error loss and fit in linear regressions. Now we can, of course, use the same technology to fit other models, such as logistic regressions. And so to do that, we'll make a binary response. If you recall in the figure with of wage versus age, there was a band at the top. Let's just get it back up on the screen. There was a band at the top of high wage earners. Let's see, where's our plot? Here we go. We'll put that plot up again. There's a band up at the top here of high wage earners, and it looks like if we threshold it around 250, we'll capture those guys, and we're going to call those the ones, and the rest are going to be zeros. So it'll be a relatively small group of ones that we're going to turn that into a binary response. So let's find our place again. Okay, and so here we are. So we can do that on the fly. Again, we use our indicator function, and there we just provide the conditional wage bigger than 250. Well, that evaluates to a true-false variable, but if you coerce that to numeric, it'll be a 0-1 variable, and so that all just happens for us here. And so that is going to be modeled as a polynomial in age with degree equals 3, and we do that, and we fit that using GLM and tell it family equals binomial. And again, we can do the summary of the fit, and it gives us a summary of the coefficients. And now, because it's a GLM, even though the polynomial was orthogonal, is an orthogonal basis, it's no longer strictly orthogonal when we fit a GLM, because there's different, GLM involves having weights for the observations, and so the orthogonality is somewhat lost. And so if we really wanted to test, for example, if a polynomial of degree 3 was needed, we'd have to fit another GLM with a polynomial of degree 2 and test to see if the two were different. We can get standard error bands as well, just like before. So we'll first make a prediction of preds, and we'll ask for standard errors. And here we do things slightly differently. We make standard error bands. Some being a little tricky here. We want preds $fit to be in the middle of the standard error bands. So that's just a single vector. And here I C bind three things together. just a 0, and I name them as well. Fit equals 0, lower equals -2 times pred dollar standard error, and upper equals +2 times pred standard error. So these are just, this is a 0 and the -2 standard errors and the +2 standard errors. So two things are happening here. These are two vectors of length n. If you include a scalar like 0 in cbind, it will just replicate it n times. So this will make a 3-column matrix, okay? And then we add to it a single vector, an n vector, and that'll just get replicated 3 times, so it adds it to each of the columns. So it's a little bit of trickery, but it's good to learn tricks. And let's look at this matrix that's resulted. We'll look at the first 5 rows, and there we see it's done exactly what we said. And so over here is the fit itself. This is going to be the lower, and this is the upper, and this is going down with values of age. So that gives the standard errors on for the fitted values. Well, actually, the predict fits the linear predictor for us. So that's on the Logistic scale. We're usually more interested in the predictions on the probability scale, especially if we fit in against a single variable. And so we want to do the conversion. So yeah, I've got an expression. We need to do the inverse logit, which I've got an expression here that's written in LaTeX. And if you know LaTeX, or here it says tech, but it's a tech language. If you know tech or LaTeX, you'll know what this means. What this is mainly showing you is that you can embed tech and LaTeX expressions in Markdown, and it'll format properly. So instead of waiting to show you the formatted document, I'm gonna run it right now. You see it runs through the whole document, and then it produces the output. Because I really want to show you what that formula ended up looking like once we formatted it with LaTeX. So here's all the output of everything we've done so far, and there we have it. So it's formatted in a mathematical formula. So if you know how to use tech, you'll know how to do that, and you'll see now you can embed that directly in the Markdown. If you didn't know about tech, don't be worried. It's a very popular language used for most people who do mathematical work, convenient way of typesetting. So we want to apply that transformation to both our fitted function and the upper and lower standard error bands to transform them to the probability scale. And so in R, this is how we do it, and we're going to apply that inverse logit function. So you see it's e to the SE bands over 1 plus e to the SE bands, or exponential of SE bands. It's going to do this simultaneously to all the elements of the matrix and return a matrix for us, which is exactly what we want here. And now we can make a plot, and so we do it. I've limited the range here because the standard error bands I knew in advance were going to be very wide, and it would have squashed the plot down. So this is the estimate of the fitted probability, and this is an estimated confidence interval, 95% confidence interval for the fitted probability. So now you see the value of doing it on the Logistic scale. The confidence bands first computed on the Logistic scale and then transformed to the probability scale. And what you get for that is that your standard error bands for the probabilities all lie within 0 and 1. So this guy never gets below 0. It's wedged in at 0, but never gets below 0. And that's kind of what you'd like, okay? And now we add some points to show where the data occur. And they'll appear. There they are. And I've actually, what I've done here is I first of all used jitter of age, because there were lots of ties in age at each of the integer values of age. To give an indication of how much data occurred at each age, I used the jitter function, which randomly adds to each element of the vector age a little bit of uniform random noise, so you can get an idea of the density. So they're the zeros, they're the ones. To have them fit on the page, since I'd limited the scale to up to 0.1, which means that we can see only 4% at most of the population in any given age category earned above 250K. We had to limit the range, we had to shrink down the ones to make them 0.1 so we can include them and just see them in the plot. Okay, so this is similar to a plot we have in the book, and it shows the fitted probability. Okay, so we've learned how to use polynomials, we've learned how to compare different polynomials, and we've learned how to plot the fitted functions with the standard error bands, and we've also learned how to use them with GLMs as well as linear models. So in the next segment, we're going to look at different functions. We're going to look at splines, which are more general functions, usually better behaved than polynomials. And we're going to see how to fit splines both with single variables and with multiple variables using the GAM package.